This video presents a short explanation on the derivation of the Taylor series and its application in determining the model variance. Taylor series in math, it helps to expand a function as an infinite sum of terms. Only condition is that one should be able to differentiate the factors in the function and that the function should be centered at a reference point like origin or 0 as a case. Before we go deep into the Taylor series, we need to understand the Maclaurin series. Let's take an equation to begin with. Say the function is fx, which is equal to a0 plus a1x plus a2x square, and this goes on till an intermediate term of ar x to the power r, and this continues till the nth term, which can be an x to the power n. Now this function has been chosen to represent a series with increasing order of x. It also has terms for which the partial derivatives can be estimated. Now for finding an expansion for this series, we need to find values of a0, a1, a2, a3 and so on. To find a0, we need to find f of 0, that is this function fx. In this function, when x is equal to 0, what is the function going to be represented as is what we need to find out. So substituting x as 0 in this function, we get all these terms as 0. So this equation becomes f of 0 equal to a0. To find a1, we have to take the first order differential of equation 1. The first order differential is nothing but a representation in terms of del y by del x. So then the equation becomes f prime of x, which is equal to 0, because when we take the first order differential of a constant, it returns 0. So 0 plus a1 plus twice of a2x plus thrice of a3 x square and so on. The nth term would become n into an into x to the power n minus 1. Now in this equation, if we substitute x as 0, we get f prime of 0 as a1, because all these terms will again become 0. Similarly, to find a2, we differentiate f prime x, this equation, and then we get f double prime x, where this f double prime, this represents del square y by del x square. So this f double prime x, this becomes twice of a2 plus 3 into 2 a3x plus so on. The intermediate term here, this will become r into r minus 1 into ar x r minus 1 minus 1. So this becomes x raised to r minus 2. Now in this equation, when we substitute x as 0, this equation returns a value of twice of a2, because all these terms again will be equal to 0. So f double prime of 0 is twice of a2. So from here we can find the value of a2, which will be f double prime of 0 divided by 2. Now if we multiply 1 to this factor of 2, we can substitute this 2 into 1 as factorial 2. So here a2 becomes f double prime of 0 divided by factorial 2. Similarly, ar can be written as the rth differential of the function at 0 divided by factorial r. So this equation can be written as f of x is equal to f0 plus f prime of 0 into x plus f double prime of 0 divided by factorial 2 into x square, and so on. The intermediate term would become the rth differential of the function at 0 divided by factorial r multiplied by x raised to r. Now, this equation represents the Maclaurin series. Like the Taylor series, Maclaurin series can also be used to expand the functions, though it goes with an assumption that each factor in the series is well defined. But in few cases, like when we expand natural log of x, if x is equal to 0, then natural log of 0 is an undefined value. In such cases, Maclaurin series cannot be used. So to counter this limitation, Taylor series is derived. So let's rewrite the Maclaurin series as function gx is equal to g0 plus g prime of 0x plus so on. It's the same equation we saw in the previous slide, but we are calling the function as gx instead of fx. Now let's say function gx is equal to function of x plus a. So if we update the Maclaurin series with gx is equal to f x plus a, we get here gx becomes f x plus a equals, here we have g0, this becomes fa. Now let's just look here, we said function gx is equal to function x plus a. Now here we want gx to be replaced by g0. So for that we need to substitute x as 0. So gx becomes g0 equals function x plus a. So x is 0 here, so this becomes f0 plus a, which is equal to fa. So that's how g0 becomes fa. And the remaining terms would follow the same pattern. So we have the function fx plus a represented as fa plus f prime of a into x, 0 becomes a, plus f double prime of a divided by factorial 2 into x square, and so on. Now to get fx here, we substitute x as x minus a. So this equation becomes f of x minus a plus a, which is nothing but f of x, equals fa plus f prime of a into x becomes x minus a, plus f double prime of a divided by factorial 2 into x becomes x minus a. So we have x minus a whole square, and the series continues. Now this series, or this equation here, represents the Taylor series. We can generalize this equation as fx equals the summation of all the terms till infinity for the nth derivative of function at a divided by factorial n into x minus a raised to n. It's also important to note that Taylor series is centered at x equals a, where a can be even 0. So this is how the Taylor series is finally derived. Now let's spend some time to understand the relevance of Taylor series in Taguchi's robust design method. This series is used in the tolerance design when we are determining tighter tolerances for the design factors. Now the estimation of tighter tolerances in turn depend on the model variance, which obviously has to be first calculated. In designs where there are number of factors and we conduct many experiments, this calculation becomes quite difficult. That's where the Taylor series is applied, with an objective to ease the calculation and linearize the non-linear equations. Now, how does Taylor series contribute in the linearization objective? Let's look at this figure. The curve here represents a non-linear function. So, if at this point xio, if we draw a tangent, then in this area the curve will be approximately linear. That is, the rate of change of slope will be 0, or we can say del y by del x is equal to 0. This first order differential representation is taken from the Taylor series to linearize this otherwise nonlinear function. With all this understanding on the Taylor series, now it will be easy for us to understand how this series helps us with the variance model in case of tolerance design. So let's say we aim to design a robust process where the response is given by y and the design factors by x1, x2, x3, xn. So the model would be defined as y equals function of x1, x2, x3 up to xn, where the model variance would be given by sigma y, the model mean would be given by mu, the factor variance by sigma I, and the factor mean by xi. Now the Taylor series is represented here. This is the same equation which we saw in the previous slides. Now if we have to expand our model, our robust design model, using the Taylor series, then we need to allocate our terms to the terms in the Taylor series. So this A here becomes mu, x becomes xi. So our model can be represented as shown here. X has been replaced by xi and A has been replaced by mu. Now this equation using the Taylor series expansion can be expanded as shown here. So the function fx becomes f mu plus f prime mu into xi minus mu plus and so on. Now is the trick. What we do here is we take the first order derivative till here. This is the first order derivative. So we take the first order derivative from this equation and apply the formula to all the selected n design factors. So this is the part of the equation we are going to be using, which is reproduced here. Now we can take this factor here, which becomes fx minus f mu equal to the right hand side. Now to calculate the model variance, we are going to rely on a term called mean squared error. If I can call that as MSE, as a function, it depends on the square of deviation of the factor level from the factor mean, which can be shown as an estimate of fx minus f mu whole square. So we can get the value of this fx minus f mu from equation 6. Substituting this value, the equation becomes the MSE for fx as an estimate of all the n factors of first order differential of the factor mean multiplied by xi minus mu whole square. which is an estimate of square of the first order differential multiplied by the summation of the squared terms of xi minus mu. Now, substituting MSE with the model variance, which is sigma y, and xi minus mu whole square, which actually approximates as the factor variance, which is sigma I, we get sigma square y equals square of the first order differential multiplied by the summation of factor variance, which is what we expand as f prime into sigma x1 whole square plus f prime into sigma x2 whole square, and so on, where f prime represents the first order differential term del f by del xi. Now, this calculated sigma y is then used statistically to recalculate the tolerances, the tighter tolerances. I hope you found the topic interesting and useful. Keep watching this space for more detailed videos from Six Sigma, DMAC, DFSS, Lean, re-engineering, theory of constraints, operations, research, etc. You can subscribe to the page and keep receiving updates as and when we upload a new tutorial. In case you want us to talk about any specific concept, feel free to contact. The contact details are mentioned here on the slide as well as on the page. So good luck and happy learning.